Hi everyone. Today's class is very important. We defined zero, singularities and residues of a complex valued function. Now first, the definition of the zero of a complex valued function. Zero of a complex function. Let f of z be a complex function and the point z is equals to z naught. The point z is equals to z naught is said to be zero of a function f of z if f of z is analytic, if f of z is analytic at z is equals to z naught and f of z naught is equals to 0. We say that the point z is equals to z naught is called, the point z is equals to z naught is called, we say that it is a zero of the analytic function or zero of the complex function or zero of the analytic function. Suppose if f of z is a complex function, here f of z naught is equals to 0, f dash of z naught is equals to 0, f double dash of z naught is equals to 0, so on, f to the power of m minus 1 of z naught, that is m minus 1 the derivative of z at z is equals to z naught also 0, and f to the power of the mth derivative of f of z at z is equals to z naught is not equals to 0, then the point z is equals to z naught is called, is the zero of f of z, is the zero of f of z of is mth order of mth order of mth order, that is mth order 0 of f of z. Suppose if only if I am taking m is equals to 1, so that means in this case what you are going to expect, if f of z naught is equals to 0 and f dash of z naught is not equals to 0, then the point z is equals to z naught is called a simple 0 of f of z, a simple 0 of f of z. This is the definition about the zeros of a complex valued function, right? Let f of z is a complex function at z is equals to z naught if f of z naught is analytic and f of z naught is not equals to 0, we say that z naught is the 0 of the complex value function. Yes, or if f of z naught is 0, f dash of z naught is 0, f double dash of z naught is 0, mth derivative of f of z at z is equals to z naught is 0, and sorry m minus 1 the derivative, mth derivative of f of z at z is equals to z naught is not equals to 0, then the complex number z is equals to z naught is called 0 of f of z of mth order or mth order 0 of f of z. Thus if m is equals to 1, then if m is equals to 1, f of z naught is equals to 0, f dash of z naught is not equal to 0, then the point z is equal to z naught is called simple 0 of f of z. Now we take the examples on this. If you take the example, first one, I am taking f of z is equals to sin z, f dash of z is equals to, if sin z derivative is cos z, at z is equals to n pi, we have the so many points are there. If I am taking z is equals to 0 also you will get, as if I am taking, suppose if I am thinking about the one point at z is equals to 0, f of 0 is equals to 0, f dash of 0 is equals to 1 not equals to 0, we say that z is equals to 0 is a, z is equals to the points z is equals to 0 is a simple 0 and sin z is analytic everywhere. As at z is equals to, in generalization, z is equals to n pi, n is equals to 0 plus or minus 1 plus or minus 2 so on. Here it is n pi are the simple zeros, infinite number of simple zeros are simple zeros of f of z. See, if you take z is equals to pi, sin pi is 0 but cos pi is not 0, z is equals to minus pi or 2 pi, minus 2 pi, like that are the simple zeros of f of z. Next if you take the another example, f of z is equals to, here I am taking e to the power of 1 minus e to the power of z whole square. Right, if I am taking z is equals to 0, you will get the f of 0 is equal to 0, that is also 0. Right, if we want to find the number of zeros of different orders, so if you take f dash of z, if you take f dash of z is equals to 2 into 1 minus e to the power of z whole to the power of 2 minus 1 into 1 minus e to the power of z with respect to z is what? Minus e to the power of z, which is minus 2 e to the power of z into 1 minus e to the power of z. Yes, if I am taking z is equal to 0, if I am thinking z is equal to 0, here this is equals to 0. Next, f of z 0, f dash of z is 0. Now I am going to find f double dash of s. Yes, here it is minus 2 into e to the power of z into the derivative of 1 minus e to the power of z with respect to z is e to the power of, minus e to the power of z. Next, plus 1 minus e to the power of z into e to the power of s, z derivative is e to the power of z, which is minus 2. You can common e to the power of z also, no problem. If you common e to the power of z, minus 2 into, here it is minus e to the power of z plus 1, here it is minus e to the power of z. Here we have minus 2, here it is minus e to the power of z minus 2 e to the power of z plus 1. At z is equals to 0, here it is f double dash of z is not equals to 0. As if you think about z is equals to 0. At z is equals to 2 e to the power of 0 is minus 2 plus 1, that is minus 1. Right, minus 1. So minus 1 into minus 2, which is not equals to 0 at z is equal to 0. What we say that? Therefore, f of z is equals to 0, f dash of z is equals to 0, f double dash of z is not equals to 0 at z is equals to 0. We say that z is equals to 0 is the 0 of order 2. Not only 0, we have the different values of z we have. If you simply in the generalization, z is equals to 2n pi I, 2n pi I, n is equals to 0 plus or minus 1 plus or minus 2, so on. If you are expanding e to the power of 0 with e to the power of x plus iy, e to the power of x into e to the power of iy, cos y plus I sin y, if you write the e to the power of z in this form, e to the power of x plus iy, e to the power of x into cos y plus I sin y, or e to the power of y, e to the power of x into e to the power of iy plus cos y plus I sin y, for taking the values of z 2n pi into I for a where n is equal to 0 plus or minus 1 plus or minus 2, so on. So these are the zeros of f of z of order 2. Here 2 e to the power of z, if you common e to the power of z here, or e to the power of 2z minus e to the power of z, like that, which is not equals to 0. Right, next, a very important definition, singular points of a function. Right, if I am taking the function f of z, let f of z be a complex function or complex valued function. At z is equals to z naught, at any complex number z naught, at z is equals to z naught, already we defined the singular points in the previous sessions also. At z is equals to z naught, f of z is not defined, f of z is not defined, or f of z is not analytic at z is equals to z naught. A function at which z is equal to z naught, f of z is not defined, and f of z is not analytic, then the point z is equals to z naught is called singular point. This is very important definition. A function is not defined at z naught, or the function is not analytic at z naught, so that the point is said to be singular point. Let us take some examples for the singular points. Example, if I am taking f of z is equals to here, or f of z is equals to, before taking the example we need one more definition here. Suppose if we have the function f of z in the rational form, yes, in the form of f of p of z divided by q of z, we may have the function numerator is a function of z and denominator is a function of z. at z is equals to z naught, at z is equals to z naught, other definition, p of z naught is not equals to 0 and q of z naught is equals to 0, we say that the point z is equals to z naught is called singular point. Let us take one example here. F of z is equals to some z plus 1 into z minus 2 by z minus 3 into z plus 2. Here it is in the form of p of z divided by q of z. That's how we can get the singular points, by taking the denominator is equal to 0. Q of z naught is equals to 0, z is equal to z naught is the singular point. So here it is z minus 3 into z plus 2 is equals to 0. That implies z is equals to 3 or z is equals to minus 2. Therefore z is equals to minus 2, z is equals to 3 are singular points of f of z. This is the definition of the singular point. Is it clear? The function is not defined or the function is not analytic, or we should concentrating on this one. The function is not analytic at z naught. We say that z naught is the singular point. Next, isolated singular point. The definition is very important. Isolated singular point. Yes, a singular point. What is meant by singular point? The function is, suppose f of z is a function. F of z is a function. Let f of z is an analytic function, or else simply I am taking let f of z is a complex function, complex valued function. At z is equals to z naught, it is not analytic. So we say that z naught is the singular point. We say that z naught is a singular point. So the function is not analytic at z naught. Okay, if you take the neighborhood of z naught, neighborhood of the point z naught, or delta neighborhood of the point z naught, yes, here that is delta neighborhood, that is nothing but z minus z naught is less than delta. This is the delta neighborhood of the point z naught. The function is not analytic at z naught. That's why we say that it is singular point. Yes, in the neighborhood of z naught we have the infinite number of points. Right, these are the points which in the closed contour are in the neighborhood of z naught, right? See, except the z naught, the function f of z, except z naught, it is analytic in the neighborhood of z naught, in the delta neighborhood of z naught. The function is analytic everywhere in the closed contour C, inside the closed contour C, on the closed contour C, on the closed contour C, where C is z minus z naught less than r, delta neighborhood of z naught, yes, is analytic at each and every point inside on the closed contour except z naught. So the point z is equals to z naught is called isolated singular point. Is it clear? Yes, the first function is not analytic at z naught, we say that that is a singular point. What is meant by isolated singular point? We isolate the point. Isolate the point means the near points all are, the closed points all are, and at each and every point which is near to z naught or which is closer to z naught, the function is analytic. So at z naught the function is not analytic. So we say that that z naught is the isolated singular point. Simple definition, right? A singular point is said to be isolated singular point in the neighborhood of z naught. The function is analytic everywhere except z naught, so that the point is called, the singular point is called isolated singular point. Let us take one example for the isolated singular points. Let us take one example here. F of z is equals to some z 2 divided by sin z. 2 divided by sin z. In this case, yes, it is in the form of f of z divided some p of z divided by q of z. The singular points are given by sin z is equals to 0. That implies z is equals to n pi. Right, z is equals to n pi. N is equals to 0 plus or minus 1, so on, plus or minus 2, so on. These are the singular points. I want to check each singular point is isolated singular point or not. First, if I am taking n is equals to 0, n is equals to 0, we have z is equals to 0 here. Z is equals to 0. So it is a 0, right? 0. This is the neighborhood of 0. If you take any point, in the neighborhood of 0 except 0, the function f of z is equals to 2 divided by sin z is analytic. So what do you say that 0 can be isolated. So we say that z is equals to 0 is the isolated singular point, not only plus 1 minus 1 plus 2 minus 2 so on. Therefore, for the function f of z is equals to 2 divided by sin z has an infinite number of isolated singular points. They are z is equals to n pi, where n is equals to 0 plus or minus 1 plus or minus 2 so on. Right, next we take the one more example here. F of z is equals to e to the power of z divided by z square plus 1. Right, if you take the z square plus 1 is equals to 0, that implies z square is equals to minus 1, z is equals to plus or minus I. Right, they are the singular points. Z is equals to I, z is equals to minus I are the singular points. Except I and minus I, the function is well defined. Not only well defined, it is analytic. Therefore, z is equals to I comma minus I are isolated singular points. Next, we take the one more example here. F of z is equals to tan 1 by e to the power of f of z is equals to 1 by e to the power of z minus 1. The singular points are given by e to the power of z minus 1 is equals to 0, e to the power of z is equals to 1. That implies z is equals to 2n pi I. Yes, just now we discussed 2n pi I. N is equals to 0 plus or minus 1 plus or minus 2 so on. Yes, for the function f of z is equals to 1 by e to the power of z minus 1 has an infinite number of isolated singular points. They are from z is equals to 2n pi I. Next, if you take the one more example, f of z is equals to tan 1 by z. Here it is tan 1 by z can be written as sin 1 by z divided by cos 1 by z. Now it is a rational function, right? The singular points are given by cos of 1 by z is equals to 0. That implies 1 by z is equals to 2n plus 1 into pi by 2, where n belongs to z, or the n is equals to, better to write 0 plus or minus 1 plus or minus 2 so on. That means from this we are writing here z is equals to 2 divided by 2n plus 1 into pi. Pi by 2 is there, 2 divided by 2n plus 1 into pi. N is equals to 0 plus or minus 1 plus or minus 2 so on. These are the function f of z is equals to tan 1 by z has an infinite number of singular points which are from z is equals to 2 divided by 2n plus 1 into pi. N is equal to 0 plus or minus 1 so on. Right, this is about the isolated singular point. Singular point means a function is not analytic at that point, singular point. Isolated singular point means simple definition is as a function, a singular point is said to be isolated singular point. In the neighborhood of that point, the function is analytic. Except this point, we say that that is isolated singular point. Now, the important concept here. As suppose if we have z is equals to z naught is the isolated singular point. The isolated singular point classifies the right. We have the isolated singular point here. Suppose in the previous class we discussed about the expanding the f of z as a Taylor series expansion or Lorentz series expansion in the given region, right? Now the important thing is the Lorentz series expansion is classifies the isolated singular point. Yes, when you are writing the Lorentz series expansion for the given function f of z, right? When we get the Lorentz series expansion, if we have more than one or more singular points are existing within the region, so we can expand f of z combination of the positive powers of n and negative powers of n. So we say that that is the Lorentz series. Here now the Lorentz series classifies the the singular points, isolated singular points, right? Suppose if I am taking z is equal to z naught is a isolated singular point, and the function f of z, the function is f of z is analytic in the deleted neighborhood of z is equal to z naught. The deleted neighborhood of z is equal to z naught is represented by 0 less than mod z minus z naught is less than r. That means if you take this is the deleted neighborhood of z naught, right? This is, then we know that the Lorentz series expansion of f of z is given by f of z is equals to summation n is equals to 0 to infinity an z minus z naught about z naught. Z is equal to z naught is a non-isolated singular point. F of z is analytic everywhere in the region R, in the region exists like this, in the deleted neighborhood of z naught. Then the Lorentz series expansion of f of z about z is equals to z naught is given by, yes, instead of Cn I am taking an here, all to the power of n plus summation n is equals to 1 to infinity some bn divided by z minus z naught all to the power of n. Yes, the first part, if you are expanding this, we have summation n is equals to 0 to infinity, or if you are removing the summation a naught z minus z naught all to the power of 0, it is nothing but a naught plus a1 into z minus z naught plus a2 z minus z naught whole square plus so on, right? Plus here it is n is equals to 1 if I am taking b1 divided by z minus z naught plus b2 divided by z minus z naught whole square plus b3 divided by z minus z naught whole cube plus so on some bm. Yes, if you take the bn or bn divided by, here it is some bn divided by z minus z naught whole to the power of n plus so on, right? If you are expanding like this, we have the Lorentz series expansion like this, right? This part is called, right, or this part is called analytic part of the Lorentz series of f of z. This is called analytic part. The function is analytic, z is equal to z naught, right? Yes, this is the analytic function. Here if the function is analytic in the region, in the closed contour, we can write the expansion. It's similar to the Taylor series expansion. That's why it is analytic part. Here it is function is not analytic. We have the terms, the what we say, the negative powers of z minus z naught. So this is called, this part is called principal part. This is very important. This is called principal part of f of z. Yes, this is the principal part, this is the analytic part, that is nothing but, yes, the summation n is equal to 0 to infinity a n z minus z naught all to the power of n is the analytic part. Summation n is equal to 1 to infinity b n divided by z minus z naught all to the power of n is called principal part of the f of z, or they are the analytic and principal part of the Lorentz series. Next. Right. As f of z is equals to summation n is equal to 0 to infinity a n z minus z naught all to the power of n plus summation n is equals to 1 to infinity b n z minus z naught all to the power of n. As this can be written as in this way, right? Just now we told that Lorentz series classifies the isolated singular points, right? Isolated singularity. That means now we define one by one here. Yes, different types of singularities we will discuss here. This is very important. The first one, removable singularity. Removable singularity. Right. Suppose in the expansion of the f of z, the Lorentz series expansion of the f of z, if the principal part do not contain any term, right? Here it is principal term, number of infinite number of terms are there. If we don't have any term in the principal part of the f of z, such singular point, in that case, such singularity is called removable singularity. In this case, the singularity can be removed, right? No term in the principal part means here this is analytic part, right? This is analytic part. This is a non-analytic part. In the non-analytic part, there is no term means singularity can be removed. Such singularity is called removable singularity. If the principal part of f of z contains no term, that is bn is equals to 0, right? Bn is equals to 0. for all n, then the singularity is called, such singularity is called removable singularity. In this case, we have the only analytic part f of z is equals to summation n is equals to 0 to infinity a n z minus z naught whole to the power of n. This type of singularity is called removable singularity. The removable singularity, we go for a pole of order m, simple pole. Next, essential singularity, that is completely based on principal part, right? If the principal part contains no term, the singularity is called removable singularity. Let us take one example here, you will get the idea. Here if I am taking f of z is equals to 1 minus cos z divided by z. See, if you see this function, what do you say? Z is equals to 0 is the singular point, not only singular point, it is isolated singular point, right? Now I am trying to remove the singularity. Here it is singularity. In this case, listen, this can be written as 1 by z of 1 minus cos z here. This can be written as, I am trying to expand as a Lorentz series, right? Here it is 1 by z into 1 minus, you know that cos z expansion, I written Maclaurin series expansion for cos z is equals to 0. The Taylor series expansion for z is equal to 0 is called Maclaurin series expansion. Here it is 1 minus z square by 2 factorial plus z to the power of 4 divided by 4 factorial minus z to the power of 6 divided by 6 factorial plus so on. This is the cos z expansion. If you are multiplying with our 1 by z of, so we can write it, this is 1 minus 1 plus z square by 2 factorial minus z to the power of 4 divided by 4 factorial plus z to the power of 6 divided by 6 factorial plus so on. So here it is minus 1 plus 1 get cancelled, multiplying with 1 by z, here z get cancelled, here it is z square, z by 2 factorial minus z cube divided by 3 factorial plus z to the power of 5 divided by 6 factorial, not 3 factorial, 4 factorial, 6 factorial plus so on. Here it is, see this one, it is a Taylor series expansion about z is equals to 0, no? There is no negative powers of z here. So, no term in the principal part of f of z is equals to 1 minus cos z divided by z. There is no term in the principal part of the expansion of f of z. So, what do you say? The singularity can be removed, right? The singularity can be removed. Before that, when we are considering the function f of z is equals to 1 minus cos z divided by z, what we have, z is equal to 0 is singular point, right? When we are expanding, singularity can be removed. So, we say that is what type of singularity we have? This is removable singularity. Singularity can be removed. Next, one more example we will take here. F of z is equals to, here sin z divided by z, sin z divided by z, right? See this, what is the singular point here? Z is equals to 0, not only singular point, isolated singular point, that is, here it is 1 by z of, right, expand sin z, here it is z minus z cube divided by 3 factorial, z to the power of 5 divided by 5 factorial minus z to the power of 6 divided by 6 factorial, not 6, here it is 7 we have, 7 factorial, so on, the expansion of the sin z, right? Here it is z get cancelled, or if you are multiplying with 1 by z, here it is 1 minus z square divided by 3 factorial, z to the power of 4 divided by 5 factorial, z to the power of 6 divided by 7 factorial, so on. See this expansion, here only analytic part is there, there is no principal part. We say that the singularity can be removed. That's why the function, the f of z divided by sin z by z has removable singularity, right? One other definition we may take in case of problems. Suppose if f of z, if you take the function f of z, see f of z is not defined at z is equals to 0 here, f of z is not defined at z is equals to 0 here. If f of z is not defined, f of z is not defined at z is equals to z naught and limit z tending to z naught f of z exist. See, limit z tending to z naught f of z is exist, we say that that is a removable singularity. If you are applying that, here in this case, if you take the sin z by z, if you are taking limit or f of z is equals to sin z by z, no? Right, z is equals to 0 is a singular point here. Limit z tending to 0 sin z by z, which is equals to standard limit extends to 0 sin x by x is equals to 1, right? It is 1 here. Therefore, it is not, even the function is not defined at z is equal to 0, but limit is exists. So, singularity can be removable. This is a removable singularity. Right, next pole. If the principal part of the Lorentz series of a function, Lorentz series expansion of f of z, if in the principal part of Lorentz series expansion of f of z contains finite number of terms, we say that here it is a pole. If it contains a finite number of terms, m number of terms in the principal part, we say that the singularity is pole of order m. Suppose if we have the principal part of the term contains b1 divided by z minus z0, where z is equal to z0 is a singular point, plus b2 divided by z minus in the principal part z minus, or suppose if we have f of z like this, the summation n is equals to 0 to infinity a n z minus z0 whole to the power of n plus z minus z0 whole square plus b3 divided by z minus z0 whole cube plus so on bm divided by z minus z0 whole to the power of m, right? Only up to term. The principal part of the Lorentz series expansion of f of z contains how many terms here? 1, 2, 3, so on, m terms, right? Yes, where here it is bm plus 1, bm minus bm plus 2, so on are zeros, right? Such in this case, if we have the m finite number of terms are existing in the expansion of the Lorentz series, in the principal part of a Lorentz series, finite number of terms when we have, we say that the point z is equal to z0, or the f of z has pole of order m, right? Here it is, we say that it is a pole of order m. The point z is equals to z0 is called pole of order m. Suppose if we have only one term in the principal part of f of z, that means f of z is equals to only one term, we have summation n is equals to n 0 to infinity a n z minus z0 whole to the power of n. This is analytic part, b1 divided by z minus z0. Only one term is there. In that case, the point z is equals to z0 is called simple pole. What do you say? It is called simple pole. If we have the two terms, it is a pole of order 2. If we have the three terms, pole of order 3. If we have the 100 terms, pole of order m. Yes, it is. If we have the m terms, pole of order m, right? Removable singularity, next pole of order m, simple pole. Simple pole means only one term in the principal part of Lorentz series expansion of f of z. Next, let us take some examples on this. Yes, if you take f of z is equals to f of z is equals to z square divided by z minus 1 into z plus 2 whole square. See, for this example, the singular points are what? That implies z is equals to 1, z is equals to minus 2. Right, z is equals to 1 is the simple pole, z is equals to 1 is the simple pole, and z is equals to minus 2 is the pole of order 2. If you are expanding this in a certain region, you will get the two terms, right? Or if you go for the partial fractions also, yes, z square divided by some 1 divided by z minus 1 plus b divided by z plus 2 plus c divided by z plus 2 whole square. Yes, it contains two terms, that's why we say that it is a pole of order 2. It is simple pole. Next, f of z is equals to, yes, here we have 4 divided by z minus 2 whole to the power of 5 plus 3 divided by z plus 1 whole to the power of 4. Yes, then what do you say? It has pole of order, has pole of order 5 at z is equals to 2 and pole of order 4 at z is equals to minus 1. Why the function is not analytic at z is equals to 2 and not analytic at z is equals to minus 1? Z is equals to minus 1 is a pole of order 4, z is equals to 2 is a pole of order 2. This is about pole of order m and simple pole. In problems we may use like this. If limit z tending to z naught, z minus z naught whole to the power of m into f of z is equals to some a which is not equals to 0, then z is equals to z naught is called, other definition, pole of order m. If you take this formula for previous two examples also. Next definition, it is essential singularity. Next type of singularity is essential singularity. Yes, if we have f of z is equals to summation n is equals to 0 to infinity a n z minus z naught whole to the power of n summation n is equals to 1 to infinity b n divided by z minus z naught whole to the power of n, right? Yes, in the previous no terms are existing in the principal part of f of z, Lorentz series expansion of f of z. So we say that the singularity can be removed, so it is removable singularity. If the principal part contains a finite number of terms, say m, we say that it is a pole of order m. If the principal part of Lorentz series expansion of f of z contains one term, it is simple pole. If the principal part of Lorentz series expansion of f of z contains infinite number of terms, right? We have the terms, infinite number of terms. In such case, the singular point z is equals to z naught is called, or f of z has essential singularity. We say that it is essential singularity. Let us take the example here. Is it clear for the essential singularity? Here the essential singularity means, yes, if in the Lorentz series expansion of f of z, the principal part contains an infinite number of terms, we say that z is equal to z naught is the essential singular point or essential singularity. Let us take f of z is equals to e to the power of 1 by z. F of z is equals to e to the power of 1 by z. Clearly what you say, z is equals to 0 is the singular point here. Why it is not exist? So if I am writing the expansion of e to the power of 1 by z, you know that the e to the power of z expansion is 1 plus z divide z plus z square by 2 factorial plus z cube divided by 3 factorial plus so on. So e to the power of 1 by z is what? 1 plus, here instead of z what is there? 1 by z is there. 1 by z plus 1 by z whole square divided by 2 factorial plus 1 by z whole cube by 3 factorial plus so on. So this can be written as 1 plus 1 by z plus 1 by 2 factorial z square plus 1 by 3 factorial z cube plus so on. See this expansion of f of z, the Lorentz series expansion of f of z about z is equals to 0, about z is equals to 0, no positive powers of z here, only negative powers of z are there, they are infinite, right? So infinite number of terms in the principal part of f of z, we say that as for the function f of z is equals to e to the power of 1 by z has essential singularity at z is equals to 0. Or in the problems we may use this formula as if limit z tending to z naught, f of z does not exist. It's in the simple way for the verification. If limit z tending to z naught, f of z does not exist, we say that Z0 is the essential singularity. Yes, in the removable singularity what I am taking, limit z tending to Z0, f of z exist, but f of z is not defined at z is equals to Z0. First case, in the pole of order m, as limit z tending to Z0, z minus Z0 whole to the power of m into f of z is equals to some constant limit a or l, which is not equals to 0. We say that z is equal to Z0 is the pole of order m. If limit z tending to Z0, f of z does not exist, it is a essential singularity. Right. Next, singularity at infinity. Yes, now we check the singularity at infinity, or to determine whether z is equals to infinity is a singular point or not for the given function f of z. Right? We substitute z is equals to 1 by w, then the function f of z becomes f of 1 by w. For the function f of 1 by w, z is equals to 0 is a singular point. It is similar to the analyticity at z is equals to infinity, right? As to check whether z is equals to infinity is a singular point of f of z or not, we take the substitution z is equals to f of 1 by w, then the function f of z is transformed as f of 1 by w. If w is equals to 0 is the singular point of f of 1 by w, we say that z is equals to infinity is a singular point of f of z. Let us take one example here. F of z is equals to e to the power of z. F of z is equals to e to the power of z. I am going to check whether z is equals to 0 is a infinity is a singular point or not. Right? In this case, here z is equals to infinity. If I am taking w, z is equals to 1 by w, f of 1 by w is equals to f of 1 e to the power of 1 by w. Clear that w is equals to 0 is what? Just now we written, no? E to the power of 1 by z. W is equals to 0 is the essential singular point. Essential singular point of f of 1 by z. So w is equal to 0 is the essential singular point, means z is equals to infinity is the essential singular point of e to the power of z, right? Or z is equal to infinity is the singular point. Let us take one more example here. F of z is equals to z square, right? F of 1 by z is equals to what? 1 by z square. What do you say? Yes, z is here it is z is equals to 0 is the pole of order 2. Pole of order 2 for f of 1 by z. In the same way, z is equals to infinity is the pole of order 2 for f of z is equals to, here it is z square, right? To check the singularity at z is equals to infinity, yes, it is same as when f of 1 by z is the having singularity at z is equals to 0, right? Yes, if f of z having singularity at z is equals to 0 of pole of order m, we say that f of z having singularity at z is equals to infinity of pole of order m. If you take z to the power of m here z to the power of m here, it is pole of order here m. This is about the different kinds of singularities, right? As based on what criteria we discussed the singularity singular points of f of z, based on the principal part of the Lorentz series. That is very important, right? Yes, if the Lorentz series is simple, in the simple way, if the Lorentz series no terms, removable singularity. Finite number of terms, pole of order m terms are pole of order m, single term, simple pole. Next, essential singularity means, yes, it is the principal part of a Lorentz series of f of z contains an infinite number of terms. So here this is the singularity. Next class we go for the residues.